as mentioned, let's look at an example. Let's put some numbers to this. So if we look at an example here, apply method of sections to an example. So a common example might be where you have some structure here, and I'll show you kind of the general shape that I'm going after here. I've got a pin on one end, a roller on the other, and I'm going to draw something like that. Okay, so I've got this thing's going to be, I'm going to draw it basically to be 20 foot long and 10 foot tall, obviously to scale, kind of. It's not going to be perfectly to scale because my drawings never are unless I'm really taking my time. But we'll draw a longer member going vertical, about the same length here going horizontal, and one more about the same length going horizontal, and then about the same height over here going vertical. Right, now when I draw a roller, I tend to just simply draw a ball. You'll see sometimes they'll draw something that kind of looks like a pin, but instead of being on the ground, they'll put it on like roller skates. You'll see those sometimes. I just normally keep it simple and just draw. Even if the book shows something like this, right? You'll find I normally just draw it as a roller. That way it's unambiguous. It doesn't look too much like this. This kind of looks too much like this to me. I understand, I get it, but this is just to kind of keep it simple. That's normally how I draw it. Anyway, there is a member that goes diagonally from here down to this pin reaction. We're going to call that A on the bottom left eventually. And then there is perpendicular right here. There's a member that goes straight this way. Okay, now this is a truss. If this was one continuous member, here to here, and we just pinned it right here, this would actually not be a truss because now I'm applying a force in the middle of this long member right here. So because this is a truss, this would actually have to be two different members right there joined at this joint. Now that may not make much sense now. Hopefully it'll make a little more sense after we look at frames and machines. That's coming next. But for the moment, just trust me that one of the earliest things when we defined a truss, we said that the forces are only applied at the end points of each member. So if I put a pin here, that means this has to be the end of this member from here to here and the beginning of this member from here to here. It can't be one continuous member, or else it's going to require a different kind of analysis. Analyzing it as a truss is actually, you're going to see, is a little bit easier. All right, I'm going to draw roughly kind of the same structure over here. Right, so we'll go one long run from here down to right there where this sits on top of the ball. We'll put a pin right above it, but then that whole thing sits on a roller. And again, this is not one long continuous member. You're going to have a member coming right here, and then where those two meet, there's going to be two different members get joined right there by a pin. So I've got 1, 2, 3 members all joined right here at this pin. Same thing up here. And then finally, I've got one member going from here to here, pinned here and pinned there. Okay. All right. We'll keep the labeling simple. Go around clockwise, lettering them A, B, C, D, E, F, and G. Or I guess you're kind of welcome to apply whatever system you want to letter them, but I try to keep it simple. Loading. How's this thing loaded? There's 500 pounds vertically down applied at point B. There's 800 pounds, a little more, 800 pounds applied vertically at point C, and then another 500 pounds vertically down at point D. So these are the forces applied to this thing. And the problem wants us to find the force in members, and it only wants 3. It wants to know in BC, CG, and GF. Now what I like to do is I like to kind of highlight or put a cross, an X on those, or somehow indicate where those are, because then it'll make it real obvious. Oh, I need to draw a cut through that. So that's a preference. That's a little pro tip, if you will, that I like to use of, how do I, sorry, I need a drink of water here. Yeah, I'm pretty visual. I have to see things. If you're visual like me, where it's like it really helps if you see it, well, I mean, this is really there for you and whoever's reading it benefits. So if it benefits you, there's a good chance it's going to benefit them. So let's just highlight these are the things I'm looking for, is these. So as we mentioned earlier, method of sections, good for finding force in specific members. So maybe somebody came along and said, hey, I think these are kind of the trouble spots. If I know the force in these, then that's going to be enough information to make some determinations. Who knows? I'm not the one that said pick BC, CG, and GF. I just borrowed this off an example problem somewhere. Okay, so let's work it through, and let's assume there's a reason we're looking for these 3 specific forces. All right, how do we do that? Well, method of sections, much like method of joints, if you can find the reactions, it's normally a good idea to go ahead and find the reactions. So let's just look at a free body diagram of the whole thing. Oh, we need to know dimensions here, don't we? As I said at the very beginning, I just kind of mentioned it quickly and we kept moving. This thing is 10 foot tall, so 5 foot from D down to F vertically, and then 5 more foot from F down to E vertically. I've not drawn that very well here. This should go all the way down. And then 5 foot spans across, a total of 20 foot across. So from horizontally, from A to G is 5 foot. From G to C horizontally is 5 foot. From C to F horizontally is 5 foot. And from F to E horizontally is another 5 foot. So again, a total of 20 foot across, total of 10 foot tall. Okay. So to find reactions, let's draw a free body diagram of the whole thing. I started to do that, and I said, wait, you can't use moment equations because we don't know any distances. Free body diagram of structure, for the entire structure. Excuse me just a second. Okay, so I drew this and I labeled it, and I realized, wait, I gotta put forces up here, so this is not a good thing, but I've drawn it all in pen, so here we are. Right? Obviously, if you're working your homework in pencil, you can just erase and move everything down, but being left-handed, pencil sometimes doesn't work so good. Anyway, I got a pen here at point A, so I'm going to draw the unknown AX, which we assume is probably going to be 0. We're going to solve that out and make sure. AX, AY, because I've got a pin there, and then I've got a roller here at point E on a horizontal surface, so that makes a vertical normal force E. And then dimensions here, so this is 10 foot, 10 foot, and 10 foot. Okay. Pause it here. Go ahead and pause it. Find these reactions. Come back to me. Okay, you got it? All right, so if you want to look at this and say, hey, Steve, I've got 1,800 pounds here. There's no X direction force, so AX is equal to 0. You've got 1,800 pounds equally distributed across here. I mean, it's not evenly, but it is equally. You probably figured out that you could take this 1,800 pounds, divide it in half, and put that on each of these two Y reactions. And it's not EY, it's just E. I've got 1,800 pounds going down, split evenly between these two reactions, so it's 900 pounds on each of them. If you wrote your equations out, you will probably find this. if you've done enough of these that you're comfortable just saying, hey Steve, that's an even, the moment equations, you can see it's just an even distribution, so it's evenly distributed between those two. Doesn't always work out that way, but in this case it did. But you should be able to, off my notes here, you should be able to, if you want to see the equations, there they are. Right? You should be able to write those equations quickly. That's the whole practice makes perfect on this stuff. Truss problems definitely get you a lot of practice on drawing a free body diagram, applying equilibrium, solving for unknowns. Now, what are we looking for? Well, I'm looking for the force in these three members specifically. Okay, so what I can do then is I can draw a cut across here. And again, if you highlighted which members you need, it makes it real easy to see, oh, I need to draw a cut right through here. So I can draw a cut right through here, and then I can draw a free body diagram of this side, or I can draw a free body diagram of that side, whichever one you want. There's no right or wrong necessarily. If you want to take a crack at it, if you want to pause here, take a crack at drawing a free body diagram of one side or the other, and then solve it, and then compare to what I do, go for it. Okay, I'm going to go ahead and work forward. I'm just going to go ahead and draw this side. There's nothing saying you couldn't draw that side, but I'm going to draw this side, the C, D, E, F side. So I'm going to draw a free body diagram of C, D, E, F there. So it's a big triangle. I've got a normal force down here of 900 pounds. That's E. I'm going to go ahead, because I'm drawing this whole structure here, C, D, E, F. I have forces applied at these endpoints here, and those are included. 800 pounds, 500 pounds. If you drew this side, you would only have this force, and you'd have the 900 pounds AY would be all that's applied to that side. And then you would have these three unknown forces. But drawing this side, you have these three forces applied to it, these three forces applied to it, and then I'm going to go through and draw these all three in tension. So I've got BC in tension. Right here in the middle, I've got GF horizontally, or FG, I guess, whichever I've written as GF initially, so I'll stick with that. I probably should have wrote it FG. If you really like things in alphabetical order, you're not going to hurt my feelings at all if you want to call it FG. That's perfectly fine. And then notice this CG is at an angle here. So I'm just going to currently draw it at an angle. Let's figure out that angle, shall we? So if we look back at the original diagram, so you've got this triangle here. Well, if you look at the bigger triangle, let's start there. If you look at this bigger triangle, this length here is 10 foot. From B to C is 10 foot, and from A to B is 10 foot. Right? And this is a right angle right here. From AB to BC, that's right angle. Meaning these angles in here are 45s. Right? There's a variety of ways you can come to that conclusion, but this angle right here ends up being 45 degrees. You do need to be able to kind of figure the trig out to get to that point. And our dimensions here, we said that this is, if you look at the original diagram, this is 5 foot, this is 5 foot, and this, I think, you can put the other 5 foot right here if you need to. I don't think we need it. I think all I need to know is that this is 10 foot across there, but if you need to know that this is 5 foot, you can put it in there. Okay. Go ahead and apply equilibrium. See, I've got 3 unknowns here. I should be able to solve for it. Give it a try. Okay, you got it? Cool. Let's see how we did. Actually, I'm going to pause. Keep this video a little bit shorter. Okay, how'd you do? This is what I did. I did some forces in the X, some forces in the Y, and I did moments about C I did moments about this point right here. Why this point? Well, because I've got two unknowns passing through the same point. If I take the moment about that point, neither of these two terms show up in my moment equation. So I can take, if you're careful about it, you can take a moment equation such that you end up with only one unknown. If you're careful, in this case I could. So by taking the moment here, GF becomes the only unknown. This equation is very simple to solve. You find GF to be a positive 800 pounds. You solve this equation here, you find CG to be a minus 566 pounds or 566 pounds of compression. Once I've got values for these two, CG and GF, I plug them back in here, solve for BC. You end up with a negative value. Be careful of your signs. This was one thing I really struggled with in statics when I took it, was keeping track of all the signs. So solve this equation for BC. So move BC to the other side of the equation. BC is the minus, it's GF already has a negative sign. The 800 pounds is already drawn in tension, so it's a positive 800 pounds with the negative sign included. The CG is in compression, so it's a negative because I've drawn it in tension up here. So it's minus 566 times the cosine of 45, and the equation already had a negative sign in it. So it ends up minus a minus. So this ends up positive, this one's negative, this one's larger than this one, so your final answer ends up with a negative sign. So BC, which we've drawn in tension, we get a negative 400 pounds. That tells me it's actually 400 pounds in compression. All right, that's a nice stopping place. We'll pick up from there.